Okay, it's time to get started. I had to go through a little stuff here, so it's also seemed to go pretty slow, which is disappointing. Okay, so you have your tests back. I still haven't even looked at what people's scores are, so I couldn't tell you what the average is or anything like that. But I think people did better. Today we're still going to be looking at relativity, and we're going to talk about four vectors and Lorentz transformations. So at this point you've at least heard the word Lorentz. You know that you have that Lorentz factor. And we're going to learn about four vectors, which are an interesting concept. So we start with, we have two reference frames. This one over here we'll call the S prime reference frame, and its variables are primed, except for I somehow clipped off the top of the Y and the prime that went there. I'm not sure how that happened, but I'll take the blame. So we have two reference frames, and we have reference S prime is traveling at speed v of S prime relative to S. Now I'm not going to write that S prime relative to S, but we need to understand that's what the V is. The V is the speed of the S prime frame with respect to the S frame, the unprimed frame. So primed and unprimed. It's a way of separating one reference frame to another. The S is the one that we're going to consider to be stationary, and the S prime the one that we're going to consider to be moving. But of course, keep in mind that we're saying relativity, which means that either reference frame is perfectly valid if it's moving at a constant velocity, and we're just choosing which one we happen to be in. Now, we're going to talk about four-vector invariance. Of course, invariant means it doesn't change. So four-vector invariants are going to be things that don't change regardless of what reference frame you're in. And there are two common ones we use, the space-time four-vector, which is what we're specifically looking at today, and then there is a similar energy-momentum four-vector. So we often, when we're starting out, we think of this four-vector as just a four-vector space-time, but there are other things that also obey the same rules that we're going to learn today looking at the space-time four-vector. So, how do we get this four-vector idea? We start with the variables that I have here in my, and of course it's the same figure and hence the same problems. The variables that I have in each reference frame are time, x, y, and z. Now in fact here, instead of time, I put CT. The CT is there for two reasons. Number one, because we sometimes consider CT to be the variable, and number two, because of what we're going to do. So two reasons for it. Let's start with the reason that makes more sense, what we're going to do. We're going to try to find an invariant. And something that is invariant is the speed of light in vacuum. The speed of light in vacuum, I forgot if it's the first or second postulate of relativity, is the speed of light in vacuum is the same in all inertial reference frames. So if I have reference frame S prime flying by reference frame S, and at the instant when their origins overlap, we're going to call that time zero. We're going to have a light bulb that flashes a light at the origin. So just to make sure we're clear here, at the instant that time is equal to time prime is equal to zero, their origins are the same place. So I have, this is back at that location at time zero. And there's going to be a light that flashes. Now in the reference frame S, when the light flashes, what happens in the time thereafter to the light? What Anne said, it goes out. How fast? The speed of light. And so we could say that the radius, it's going out in all directions of the speed of light, so it's going to make a circle or a sphere in 3 dimensions. And the radius is going to be equal to the speed of light multiplied by the time that has passed since time equals 0. Does that make sense? The light is traveling at speed c. We have time t that's passed. It's out that far. But we can also use geometry to calculate the radius. If we use geometry to calculate the radius, what do I get for the equation for radius of a sphere? You have x, y, and z are components. A point on the sphere has variable, okay, let me just mark it on here. So I have some point on the sphere that has x, y, z as its 3 spatial components. So how do I find the radius out to that point? You use the 3-dimensional equivalent to the Pythagorean theorem. Right? The Pythagorean theorem is just 2 dimensions. If you go 3 dimensions, all you have to do is do Pythagorean theorem in 2 dimensions, and you'll have one side is square root of x squared plus y squared. And then you take that squared plus the z squared. You have x squared plus y squared plus z squared is the radius. So it's going to be the square root of x squared plus y squared plus z squared. Now I have radius on both sides. I'm going to square it. Why? To make my life easier. And so if I square this, of course, r squared is equal to c squared t squared. And r squared is equal to x squared plus y squared plus z squared. So if I set those radii equal to each other, because the truth is I don't care about what the radius is. I want a relationship between x, y, z, and t. We're not going to have clear questions. So I'm going to set the r's equal to each other so I don't have r that I don't care about. And I have c squared t squared equals x squared plus y squared plus z squared. Let's say instead of looking at this reference frame S, I looked at my primed F reference frame, S prime. What would I see happening to the light in that reference frame? Would it still be traveling at the speed of c in all directions? Yes. So would it still make a sphere? Yes. And so would Pythagorean's theorem still apply? Yes. And so that means I'm going to have the exact same relationship, c squared t prime squared equals x prime squared plus y prime squared plus z prime squared. Well, we have something here now that looks the same in both reference frames. And so we actually rearrange this. We say 0 is equal to c, well, I'm going to put parentheses. It makes my life easier. And we now have the basis for an invariant. Left side is a constant. It's invariant. It doesn't matter what reference frame you're in. It's always going to be 0. And the right-hand side is relating the time, the x, the y, and the z. So this is a 4-vector invariant. And the work that we're going to derive from here on out is the same for anything that you can define a 4-vector invariant. Now, it does not have to be 0 on the left-hand side. For instance, for the energy momentum 4-vector, it's not 0 on the left-hand side. But it's invariant. There's a quantity that's going to be the same in all reference frames. Now, the next slide goes through probably next 3 slides go through what I've just done. This is talking about we could do it in time or in space to calculate the radius. And then equals 0 for the invariant. And so here is our invariant. And now we have something that's a little bit tricky. Everyone knows how to do a dot product in this class. a dot product, if I had vector, let's say vector A equals 5, 3, 2. What that means is it's 5 in the x direction, 3 in the y direction, 2 in the z direction. And vector B is equal to 6, minus 1, 4. How would you calculate A dot B? Don't need a matrix for this. This is an inner product. Don't need no matrix for an inner product.
Inner product.
Yeah. Well, one way of doing that, I thought everybody would know the answer.
Well, I'm assuming
What-
that's what's at the very bottom there, but
It's not what's at the bottom. That's why I'm going through this part first. Okay, what would,
You're in essence multiplying parallel parts.
you're multiplying parallel parts.
So
So,
just multiply the complement?
so you multiply 5 by 6
Okay, so
plus 3 times a minus 1 plus 2 times 4. And that's how you would find the inner product, the dot product. Now you can write it out as a column vector and a row vector, and usually the way you would do that is you'd say, well, I'm going to convert B into a column vector. And so I would actually, I'm going to move this down so that it's not on top of stuff. Of course, I didn't get it all the way, but the wonder of memory is another one.
what is it?
The wonder of layers is that these are on different layers, so I can move one without respect to the other. Okay, so, by the way, 30 minus 3 plus 8. So 30 minus 5 is 25, right? So there, just to finish it out. Normally when I do this dot product, I would put it as 5, and now I'm not putting the commas, a row vector times a column vector, and the column vector I just transpose the numbers. And then we use, what was that?
So it was the one that was at the bottom.
Not exactly. There's a difference, which is why I'm going through this. So we can understand what the difference is so we don't get as confused when we see inner products. So now we would take this, and for multiplying matrices or vectors, the first one, second one, third one. And so it gives you the same thing. And so that's how you would write A dot B traditionally. Well, with the 4 vectors, we don't just transpose to go from a column to a row. The reason is because we have a plus sign here and minus signs there. And we have to have something to account for that. There are different mathematical ways of accounting for it, and one is just to define an inner product for 4 vectors. Right, so it's not the standard inner product, it's the one for 4 vectors. And, well, it's actually, I should go back. It's defining how 4 vectors convert from a column to a row matrix. And the rule for that, the one that I'm going to teach you, is that when you go from a column vector to a row vector, the first element stays the same sign, the next 3 change signs. So here, right, instead of having, if R is CT, X, Y, and Z, then the column, or the row vector for that, CT is the same sign, but I change the signs for each of the ones after that. And then you multiply them through as we did here. So what's the difference? Why did I go through all of this? So we understand the conversion here from the row vector to column vector involves those minus signs.
What is that you're doing there, though?
What am I doing? This,
What is
this right here?
The R vectors.
Okay, So the r vectors are the radius for that circle of light.
Okay, so why can't we approach it the same way you did the A and B vectors?
Because in our invariant we had minus signs there. And in order to affect those minus signs when I do the dot product, I needed to have the minus signs appear when I convert from a row vector to a column vector, or from a column vector to a row vector. So I used the same multiplication rules, this one times this one plus this one times this one plus that one times that one. But the signs were shifted in the conversion from column vector to a row vector.
I guess I'm just lost on. Okay, so first of all, we're doing r dot r because
r dot r is what actually gives us our invariant.
And where did we come up with the invariant in the first place then?
That was the previous calculation, where I calculated the radius in time, space, and the radius in position space, and then set the radii equal to each other, and that gave me this invariant.
Okay.
Now, one last thing on this before I go forward. We will not see this again in our lecture, but many times people take this and they say, let's call this vector here x0, x1, x2, x3, which means that x0 is CT, x1 is x, x2 is y, x3 is z. It's easier in your nomenclature to write it that way. Since we're only doing one lecture on this, we're just going to leave it as CT and not call it x0. Why do they make this conversion? What are the units of CT?
Meters.
Meters, distance. So we have the same units for everything in our x's. Common unit makes more sense. And then we can do our math using things like, Einstein summations and, the index 0, 1, 2, 3 makes some sense. So we're not going to do that, but I want you to see it in case at some point you read a book on relativity or particle physics, which relies on relativity calculations, and you see that, you want to know, what does it mean? So what's the point of all this? We have a 4-vector invariant, and we have a mathematical way of calculating that it's invariant. So let's go forward from that. We've learned about transformations for time dilation and length contraction. Let me write those down just to make sure that that's in the top of everyone's mind. Delta t is equal to gamma delta t0, not delta. Uh-oh, wasn't supposed to happen. Come back. L is equal to L0 divided by gamma. What does it mean if it has the subscript 0?
It's the true version.
Let's not say true, let's say proper. Because they're all correct. And true implies correct versus false being incorrect. But they're all true. But proper is the limiting case. The proper time is the shortest possible time between two events. For any person in the world to make the measurement, the proper time is the shortest time. And the proper length is the longest distance between two things that can be measured by any person.
And gamma is 1 over the square root of 1 minus...
Yeah, gamma is that Lorentz factor of 1 over the square root.
Why is it always written as b squared over c squared when it's
Well,
almost all, at least so
we
far,
usually
we use it as b over
we
c?
oftentimes write it like this, where beta is v over c, because it's a lot quicker to write that way. Is that what your question was?
Essentially.
Yeah. Because physicists don't like to go the long way. They like to go the short way. So we usually write it more like this, but our textbook doesn't. Why? Because we're introductory class. You only have like one chapter, and they figure it's not worth the time to introduce a new variable for something that you understand well. Right? You understand V, you understand C. Okay, so given this, these time dilation, length contraction, we should be able, wow, I am not moving it, just, we should be able to come up with some conversions for a 4-vector to relate the x0, x1, x2, x3, or the time x, y, z with x0 prime, x1 prime, the time prime, the x prime. That's what we're going to work to doing. That's what the Lorentz transformations are. So, given that we have a linearity in our transformations for proper time, time dilation and length contraction, then it should be clear that we should have a linear relationship between the time in one reference frame and the position in time in another reference frame. Likewise, a linear relationship between the position in one reference frame and the position time in the other reference frame. So our goal is going to be to find these constants A, B, C, D for the conversions. And it's kind of nice. If you take a higher level class, it becomes kind of important to do this as a matrix. Why is a matrix? Because it makes calculations quicker. Now, for you, in general, that's not going to be the case, right? We're just learning basic things. But if you're actually doing significant calculations, that matrix idea is important. Now, this is only showing a 2 by 2. Really, it should be a 4 by 4, right? Because we should have y and z. So there is another thing that is not mentioned, but that's implied. V, what was V actually the speed of? It was the speed of the S prime frame with respect to the S frame. That was, you weren't here when I defined it. So V is the speed of the S prime frame with respect to the S frame. And we're going to set V is in the X direction. So we define, what we're doing here is defining the X direction to be the direction that the S prime frame is moving with respect to the S frame. Right? Because you have to define your direction some way. And we just choose to say, okay, whatever direction that one's moving with respect to this frame, that's my X direction. Why do we do that? Because in which direction do you have length contraction? Only in the direction parallel to motion. And so we only have x prime different from x. We don't have y prime different from y or z prime different from z because we defined the direction of motion as x. So I could have extended this. I could have said t prime, x prime, y prime, z prime equals AB 0, 0, CD 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. I could have done that. But this stuff here that's all zeros and ones is kind of not helpful to me. It just tells me something I already knew. And this is something that we also do in physics. We want to take shortcuts. We're like, we don't need that stuff, so let's not worry about it. It exists in reality, but we don't worry about it. When you take particle physics, you find other things we do that gets a little more intense, like having a 2 by 2 matrix, but each element of the matrix is, well, you start with it being a 2 by 2 matrix. You end up with each element being a 4 by 4 matrix. Yeah, it was not as fun as I thought it would be. So, actually, I'll leave that there just in case you want to come back and look at the notes. So we want to try to find what these constants A, B, C, and D are. So we start by taking what we already know how to do. That is, we know that we're going to have the length from the origin of the S frame to where some event happens has to and so that's this part here that I've marked in X. It has to equal the distance that the S prime frame has moved with respect to the S frame. So that's the speed multiplied by time, as measured in the S frame, plus Once again, that's this. Plus the contracted length from the origin of my S prime frame to where the event occurs. So this here is my contracted length, X prime, the contracted length, or excuse me, yeah, the contracted length is going to be X prime over gamma. X prime is the length that it would be in that reference frame. Contract that to find what it is in this frame. And so that's just saying the distance as measured in the S frame is equal to the distance measured in the S prime frame contracted because of length contraction plus the distance that prime frame has moved. So we just take this and solve it for X prime. Now, I'll actually show the math to solve for X prime just to make sure we're all on the same page. So I have my equation X equals Vt plus X prime over gamma. The first thing you want to do is subtract Vt from both sides. So then I'll have X prime is equal to X prime over gamma is X minus Vt, and then clearly I multiply both sides by gamma. And I'm left with X prime is equal to gamma times X minus Vt. Or, since the equation I had was in the form X prime equals AX plus BT, then I can write this as gamma X minus gamma VT. So I can read off from here, there's my A value, and there's my B value. Put a plus there so that it doesn't look like I've messed up signs. So from my preceding page, I think that was, whoops, it was C and D. Okay, I'm going to still write them here. There's what we just found. I need to go back and change from A and B to C and D to get these symbols matching. So there's half of the elements for the matrix. For the other half of the elements of the matrix, I will take essentially the same situation, but run it in reverse. So the distance measured in the prime frame, X prime, is going to be equal to minus Vt prime Y minus, because if I go into the S prime frame, the speed of reference frame S is in the opposite direction. So it's in the minus X direction, hence the minus sign there. And then plus X over gamma. Why do I have a length contraction equation again? Because I'm now looking at a length as measured in another reference frame, that in that reference frame, starting at any points are stationary, I have to contract it to get it to mine. And so taking this equation and replacing the X prime with what we found from the preceding page, or the preceding work, we have this here is what I just substituted, and then equal to what's up above.
So this is the equation for the position?
Our goal here is to find the equation that says T prime is equal to A times, AX
So this is for the
plus
time frame?
BT. This is to relate the time in one reference frame to the time in another reference frame. Not the time between two events, but the time.
We have two of the similar equations. What was
The other one, the one that we did on the preceding page, was x prime is equal to cx plus dt. That's what we did on the preceding page. That was for x prime. This one's for t prime.
We had the same one, but without the negative.
Well, the result that we found was this right here. Okay, what are we trying to do? We're trying to find t prime. So we substituted for x prime so that the only prime variable now is t prime. So now you have to go through a little longer math. You have to add or subtract x over gamma from both sides. So you have minus vt prime. Then you have to divide by minus v. And you solve for t prime is equal to, so here's the first step. Those two steps combined actually right here. And then a rearrangement. This rearrangement is the thing that I had to spend some time thinking about. I have in my first term xv over gamma. In the second term, I have an x gamma over v and a gamma vt over v. Well, the v's cancel. I have a gamma t. What I did is I factored out an x gamma over v. So if I take this first term, xv over gamma, if I factor out x gamma over v, it was xv over gamma. Well, I brought out the x, so that's no problem. But the gamma was on bottom, and I factored out a gamma on top. So what do I have on bottom now?
Gamma squared.
A gamma squared, because I factored out one gamma, and I need to be left with one gamma on bottom. And then on bottom I had a v, and I'm factoring out a v, so that's it for that one. Now for the second one, I have minus gamma. Okay, so that gamma and that x, those come out. That v comes out, and this entire term, the gamma x over v, that's just minus 1. And then the final term is going to be a minus makes it a plus, and then I have a gamma vt over v, so that's just gamma t. So that was the work to get to the middle form. But then we recognize this thing right here, 1 over gamma squared minus 1 is equal to, since gamma is, do you have a hand up? No, okay. Since gamma is defined as 1 over square root of stuff, invert it, so I'm going to have the square root on top, square it, and I get rid of the square root. So this first term is just 1 minus v squared over c squared minus 1. Well, 1 minus 1. I'm pretty good at math. I'm pretty sure those add up to 0. So this stuff in parentheses just turns out to be minus v squared over c squared. And so now I do another, I should have written that in a different color just to set it off. Another factoring, I'm just going to factor the gammas out now. So my first term, and I'm going to write the intermediate because we don't have the intermediate. And so I'm just going to factor out the gamma. And I'll take the last term first. That was just a t. Minus sign here makes it a minus. Factored out the gamma. I still have an x on top. V squared divided by v gives me 1v on top divided by c squared. That was a lot more work. But now we have our a and our b. I re-expand it. And it doesn't look right until I do the last part, because I have plus minus there. So there's A and B. So we now have our A and B. From the preceding work, we had the C and D. Now we have everything we need for our matrix. Question, Chad?
Your gamma on B go.
My gamma, that was a mistake. Thank you. It is important to be correct on these things or you end up with all kinds of wily, crazy things.
I think you don't need it in the top part, right?
Don't need it where?
The second one you just wrote, because you've got gamma multiplying everything.
Yes, I don't need it there. Did I just write it there? Okay, yes, like this. Too many mistakes make Richard sad. So here it's summarized now. Here's the two equations that we found, and thus the matrix we made with the A, B, C, and D. Now when you look at this matrix, one of the things we don't really like is it's not really symmetric, right? By not really symmetric, I mean it's not symmetric. But what can we do to make this symmetric? If we put a CT there and a CT there, then that is going to make this, I think it goes like that, right? I actually didn't think it through very carefully. Let's see if that works out. CT prime is equal to gamma CT prime minus VXCT over C. Actually, I'm not going to write it that way because I didn't think it through too. I'm going to do this instead. Yes, that was indeed the correct for that. And for this one here, and so, yeah, I was correct. So if I put the C with the T, then it becomes symmetric. Another reason why we want to use that CT, it brings in a natural symmetry to this conversion relationship. So, now we actually have our conversions. Taking what we've done, we can do our conversions now between the unprimed frame and the primed frame using what we've just found. What is beta? V over C. So what we've taken is this, right? That's what we had on the preceding page when I made the substitution. We said, well, V over C is clearly beta, right? That's our definition right here that I talked about earlier in the lecture. And so we just replace and x1 is x, x0 CT. And so we have conversions, and these here are the Lorentz conversions. The ones on the left are from converting from the unprimed frame into the primed frame. That is converting from the frame I'm in to some other reference frame. The ones on the right are converting from some other reference frame into my reference frame. The only difference is the sign here. Why the sign? We've already talked about that. Why did that sign change?
Because of how we multiply the four, or not multiply, when we have like the row and the column.
It's actually not. It's because in my reference frame, that thing's moving that direction. In its reference frame, I'm moving the other direction. So that's why you have those sign switches. Notice the X x2 and x3. That's the y and the z. Those don't change because you only have length contraction in the direction parallel to motion. So now we can take an event like graduation, which has a specific time, a specific x position, y position, and z position, and some other reference frame, we could calculate the time and the position by using these Lorentz transformations. Now, for such a case, for graduation, you're probably not worried about it, right? We're not going to have somebody buzzing by trying to watch graduation for the split second that they're buzzing by at relativistic speed. Right? So it's not really a relevant concern. But when you start talking about what's going on with particles and their interactions, it becomes a very relevant concern. Now, what's the goal of today? The goal of today was two parts. Number one, getting these conversions, the Lorentz transformations. These same transformations would work if you changed it from the space-time 4 vector to the energy-momentum 4 vector. The energy-momentum 4 vector is actually we use P. That's the energy-momentum 4 vector. E0. What is E0? It's called the rest energy, and it's mc squared, right? Einstein's famous E0 equals mc squared. A lot of times people drop the 0, but it's not correct if you drop the 0. Right, you have E0 equals mc squared. E is equal to gamma mc squared. Oh, wait, no, that is E. That is E. It's the invariant that's the E0 over C. My mistake. It is E over C.
Wouldn't that just be gamma MC?
Yes, it is gamma MC then. But I put it the E over C so you can see how energy relates. Because if you put gamma MC, you don't see the energy per se. That's scary, though, that I made the mistake.
Can you go down just so
You know these are like on Moodle, so you can...
Yeah, but I can take notes directly.
Okay. Just make sure. Okay, so the first step was these Lorentz transformations. The second step, velocity addition. So we want to calculate how velocities add. Now we've seen the equations for them in the other class with really no justification whatsoever. But now we can do it. We can do the math ourselves. So we define ux, the speed of object x, in reference frame s, is dx dt. Make sense? Should, because we've talked about that since like the first week of first semester. Ux prime, the speed of object x in the s prime frame, is dx prime over dt prime. Right? The laws of physics have to be the same in all reference frames, so in the prime frame it's the same equation, we just put primes everywhere. Well, we want to use this to find what ux prime is in terms of the unprimed variables. So ux prime, that's not a prime, is equal to dx prime over dt prime. Well, x is this equation. So what is dx if that's x? Not dx dt, not dx dy, but just plain old dx. By the way, keep in mind v is constant for these transformations, so you don't have to worry about gamma or v changing. Okay, we'll start with gamma. X becomes... I'm doing the derivative, not the derivative with respect to something. What do they call it? Improper? I don't know. I don't remember the name for it. Okay, implicit. So what do I replace the x with?
1.
Not 1. Not 0. dx, yes. And find the infinitesimal change in dx prime is equal to gamma times the infinitesimal change in dx. What's next? Minus v what? dt. V times the infinitesimal change in time. Now let's look at t prime. What am I going to get if I do the same thing for the t prime? Go ahead, Sally. Lay it out. I'm taking this equation here,
Oh, that equation.
and I'm taking the implicit derivative of that. What am I going to have?
Gamma dt minus x.
X is a variable.
Oh, right. B over c squared dt.
Not t.
Oh, d.
dx. That was an x.
Oh, yes.
Okay, so now, am I done? No, of course I'm not done. I have dx's and dt's everywhere. But now that we've done this implicit differentiation, we're just going to take each top and bottom and divide them by dt. Remember, derivatives aren't truly fractions, but we treat them that way. And so if I divide top and bottom by dt, that's just multiplying by 1. There's no big deal, right? That's totally legit. But then this becomes gamma times dx dt. What's dx dt according to my definitions?
US.
Minus v. And what's dt dt? Jaron, you're on top of this. 1. On the bottom, Michael, what do I have on the bottom now? Start with the obvious. And then I have dt divided by dt. That's minus v over c squared dx dt.
dx dt is ux.
And so now, to complete the work, notice the gammas are going to cancel. And I have ux prime is equal to ux minus v over 1 minus vux over c squared. So this is our velocity transformation equation. Now, it looks different than what we did in class for one very simple reason. In class, I did subscripts for both of them, and I did the velocity in the order that made this a plus sign and this a plus sign. Right? It just depends on which reference frame to which reference frame what that sign is. So it really is the same equation. Yes?
What's the velocity again? In this?
Okay, in this equation, v is equal to the velocity of s prime with respect to s.
And u is the speed.
And
It's not there anymore. But
u is equal to the velocity of x with respect to s. ux prime is the velocity, or I'll just put O for my object actually, of my object with respect to s prime. And so putting those definitions in, our equation is velocity of the object with respect to s prime is equal to velocity of the object with respect to s minus the velocity of
respect to s.
s prime with respect to s, excuse me. Screwed that up.
Wait, don't you want S to S prime on that top one?
I do. That's why the signs are different.
Okay. No. What?
I want this to have the same in the middle for the plus sign. This has a minus sign, and these indices are in opposite order. That's why the sign is opposite what we learned in class. This is what we learned in class. But that's equal because I switched the order of these two, and that changed the sign. And for my last trick, because we're out of time, I need to go to my last trick. Uy prime equals. We did not have in the other class what the velocity of something moving in the y direction is going to be. So what this is saying is I have reference frame S prime, and I have something in reference frame S prime that's moving in the y direction, perpendicular to the motion. And I'm asking what that velocity is going to be in my unprimed frame. If it was distance, it would be the same. But velocity is distance over time, and the time is still contracted. Or excuse me, dilated. Distance, yeah, time is still dilated, so it's not going to be the same speed. If it was, you would have crazy things like an object is moving this direction at speed v and shoots a photon up this direction. Well, the photon, as viewed by another reference frame, is going to be pointing in that direction, and what's its speed? And you would come up with the bigger than the speed of light. So it can't be the same speed. So what we have to do here is we have to say, well, it's going to be dy prime dt prime. Well, dy prime was really simple because y prime equals y. So what's dy prime equal to? dy. dt prime we already did. So I'm just going to take what we had from above and copy it again. Gamma dt minus v over c squared dx. What did we do the previous time to finish it out? Divide top and bottom by dt. So over dt, over dt. The top is dy dt, which is uy. The bottom, gamma dt dt is 1 minus v dx dt, not dy dt, dx dt. So that's going to be ux over c squared. So there's my equation for addition of perpendicular velocities. And of course, there's no point in doing dz because the only difference would be on top of it would be uz instead of uy. We are 2 minutes over time. Any questions, my friends? How about my enemies? My neutral people? My frenemies?
Hopefully no one can ask it.
All right. Have a good day. I'll see you again in lab.